Greetings everyone. Today I'll be talking about a topic that we've been exposed to in our analog and digital communication course. It's related to quantization. So the nature of most of the signals we have in our universe is of an analog type. But for our computers to be able to process them, we have to get them into some form of digital format to represent. So what we do is we can use many techniques like pulse code modulation and delta modulation. Using these schemes, we can actually extract our message signal at set intervals to obtain certain discretized values, and this process is known as quantization. Suppose I have a message signal m of t which is analog in nature. What I do is, using a modulation scheme, I can extract the signal at particular intervals, and these particular intervals are known as quantization levels. So I would denote in the start what would happen is that the number of quantization levels is fixed, and it lies between certain peaks, which is m of p and minus m of p. The number of quantization levels I have is equal to L, and you can see here by the division that this is the number of quantization levels. And the magnitude of the subinterval, or basically the difference between any two quantile intervals, is actually delta V, and this relation is such. I won't get into the derivation of this because we're making this video for practical purposes of solving any questions related to quantization. So what happens is that if you have this magnitude of difference between two quantile levels, you can actually characterize the error you can encounter when quantizing. So the error is obviously limit to plus minus delta V by 2. This is the magnitude of the error we can encounter. But for practical scenarios, what we want is the power of this quantized level. So what happens is that if I want the power of the error, I'll denote the power of the error as q squared bar. Using the Nyquist theorem and orthogonality properties, I can go on to derive this expression for the power. But due to the scope of the video, I'm not going to get into the derivation right now. But the final value for the power of any noise, of a quantile noise, is such, where L is the number of quantile levels and MP is the peak magnitude of the quantization. So basically, this is the benefit that we get from this is that we get a compact form for to display our noise power. So for practical scenarios, what we want to do is obtain the signal to noise ratio. If you are actually transforming an analog signal into a digital format, you have to know what is the ratio of the signal to the noise. So what I say is that the signal to noise ratio is actually the message power divided by the noise power, which is intuitive and makes sense. So using the above relations, we can actually establish the fact that the signal to noise ratio is of the following type, which is the expression for the signal to noise ratio of a quantization. So now that we've covered this, I would also briefly like to talk about a topic that we use a lot in digital communication, which is related to the logarithmic scales. Logarithmic scales have many advantages, and I'll talk a bit about them, but first I'd like to actually define how the log scales actually work. So we've all heard of the decibel scale. What the decibel is simply the relation of 10 into log to the base 10 of any signal to noise ratio, right? So in practical scenarios, we're actually concerned with finding out the power in decibels. So the power in decibels is actually of the following format. Again, 10 into log to the base 10 of a particular power of 1. So this factor of 1 is actually a reference value of 1 watt. So power in decibel watts is actually a power in decibel with a reference value of 1 watt. Another commonly associated parameter that we use is power in dBm. So the dBm in power, just like the power in watts is with a reference of 1 watt, so the power in dBm is actually with a reference of 1 milliwatt. So why is this advantageous? That I'll actually explain why we even use the log scale. So in communication, we often have to deal with very large values like in gigahertz frequencies or bit rates, or extremely small power values like the input and output levels of channels. So the logarithmic scale actually provides us with a lot of convenience in handling all these values. And since signal powers are often encountered in milliwatts, the PdBm scale is actually very useful for us in practical scenarios. Now we'll go on to solve some questions to help you get a better understanding of how this process works out.
Hello and assalamu alaikum. My name is Sunny Hamid Alfi and I will be solving few problems in this video. The problems are basically taken from the book Analog and Digital Communication by B.B. Lathi. Is from chapter 6 section 6.2. Basically, if you haven't read B.B. Lathi, so basically chapter 6.2 covers quantization level, bits per second, channel bandwidth. So basically we will be solving problems which involve these things. So let's start with the problem. So in the first question that I have in front of me, I have already resolved it, but I will be explaining it to you that how did I solve this problem. It's not difficult, so let's you need to just pay attention here and concentrate here, and it will be very easy for you to understand here. So the question says that the American Standard Code for Information Technology has 128 characters. So basically, it is saying that the code is divided into these number of characters. So basically, these are the levels, quantization levels that is being given to us. So because he's dividing the code into certain parts, certain levels, and that are 128 here. So that are the number of levels, so which are binary coded. If a certain computer generates 100,000 characters per second, determine the following. So the 100,000 characters per second is not the bits per second. This is the sample rate. This is the basically the frequency that is given to us. The bandwidth is given to us, which is 100,000, because you need to be very careful with the bits per second and samples per second. There are two different things there, so just you need to be careful with that. So it means that it's generating around 100,000 characters per second. That would be the frequency here. So let's move to part A. Part A says the number of bits required per character. The number of bits are denoted by the letter N here. So to calculate that, it's very easy. If you know the number of levels, that is 128. It's not difficult. You just need to plug in the formula, that is N is equals to log 2L. L is the quantization levels. Plugging the values, and you can use the calculator to calculate it. It turns out to be N is equals to 7. So you can see it's quite easy. Now let's move to the next part. The next part says the number of bits per second. So you can see now it's saying to calculate bits per second to transmit the computer output and the minimum bandwidth required to transmit the signal. So it's basically part B has two parts, 1 and 2. So we'll first solve the first part. So the first part says that we have to calculate the number of bits per second. So to calculate the number of bits per second, there's a very general formula, which is sampling rate into number of bits. It's right here. So the sampling rate is given to us as 100,000, which was given to the question. Number of bits were calculated in the previous part. Multiplying these both will give us the bits per second, which turned out to be 700,000. If you know the number of bits per second, it's very easy to calculate the channel bandwidth. Just dividing the value by 2, the bits per second by 2, will give us the minimum channel bandwidth, which turns out to be 350,000 hertz here. So now let's move to part C. Part C says here, for single error detection, Gibelin addition bit parity is added to the code of the character. Modify your answers in part A and B in view of this information. So you can see that we have added another bit. So the modification that part A and part B would have, simply part A would be quite easy. The number of bits previously was 7, so now increasing the n by 1 increases the bits to 8, so that would be 8 bits per character. That's quite easy. And the next part, now you can see here by modifying part A, part B also modifies it, because to calculate the bits per second, the formula was sampling rate into n. If number of n has increased, so is the bits per second, and if the bits per second has increased, the channel bandwidth will also increase. So we'll use the formula, bits per second is equal to sampling rate into n, which turns out to be 100,000 into 8, that's 800,000 bits per second, and again dividing by 2 will give you the minimum channel bandwidth there. So you can see it's quite easy. Now we will move to the next question. So after solving the first problem, now we're solving another problem. This is a bigger problem, and this will make your understanding much better. So now let's read the question. It is desired to set up a central station for simultaneous monitoring of electrocardiograms of 10 hospitals. So here in the question it says that we have 10 hospital patients. Data from the rooms of the 10 patients are brought to a processing center over wires which are sampled, quantized, binary coded, and time division multiplexed. So the data from each patient is being multiplexed, and that is the multiplex data are now transmitted to the monitoring station. So all the data is being multiplexed and passed through a single line. The ECG signal bandwidth is given to be around 100 Hz. The maximum acceptable error in sample amplitude is 0.5% of the peak signal amplitude. That is the quantization error that is given to us. Error. The sampling rate must be at least twice the Nyquist rate. That is very true, because the sampling rate is always greater than the Nyquist rate, because the Nyquist rate is the frequency that we can work with, that is the required frequency, but we always take it greater. So due to some noise or due to some problem, our signal is not disturbed. Now we have to determine the minimum cable bandwidth needed to transmit this signal. So first we'll divide the question in few parts. So first we'll calculate the Nyquist rate. So to calculate the Nyquist rate, it has a very basic formula, that is, it is always twice the bandwidth. The bandwidth is 100 Hz, so multiplying it by 2 will give us the Nyquist rate. That is the samples per second here. So as I told you earlier that the sampling rate is always greater than the Nyquist rate, and then the question says that it must be at least twice the Nyquist rate. So to calculate the sampling rate, we will multiply the Nyquist rate by 2. Into the Nyquist rate, which is 200 here, multiplying it by 2 will give us 400 Hz. So here we have the sampling rate as well. So now let's move towards the quantization error. So the quantization, to calculate the basic formula to calculate the quantization error is quantization error is equals to peak amplitude divided by the number of levels. So here we are given that the quantization error is 0.25, that is 25 over 100 into the peak amplitude, which is MP here. So that is the quantization error, which is equals to MP over L. So from here you can see the MP will be cancelled out, and from here we can calculate the value of L. So we can calculate the value of L from here. So let's cut this out. That would be 0.25 is equals to 1 over L. So L would be 400. So here you can see we've calculated L. L is the number of levels. So now after calculating L, now we can move to calculate the number of bits. So because you know, if we know the number of levels, L is 400, so we can easily calculate the number of bits. So the formula to do that, as I've told earlier, is n log 2 of L. So from here we can get n to be, so let me use my calculator. So n would turn out to be 9 here. So now we know the number of bits as well, we know the sampling rate, we know the Nyquist rate. So now from here we can move on to calculate the bits per second, because by calculating bits per second we can then calculate the channel bandwidth. So it will be very easier to calculate channel bandwidth if we first calculate the number of the bits per second. So to calculate the bits per second, we'll use the formula, which is sampling rate into n. So sampling rate is 400 Hertz, multiplying it by 9 will give us around 36 kilobits per second. So now the next step would be to calculate the channel bandwidth, which will be bits per second divided by 2, which will give us 18 kilohertz. So this will be the channel bandwidth. I hope you understood this question. It was quite easy. Now let's solve this problem. So this will be the last problem that I would be solving. So the output SNR of a 10-bit PCM was found out to be 30 dB. So we are giving the signal to noise ratio here. The desired SNR is 42 dB, and we have n is equals to 10 for 30 dB. It was decided to increase the SNR to the desired value by increasing the number of quantization levels. So by increasing the number of quantization levels, the number of bits will also increase. Find the fractional increase in the transmission bandwidth required for this increase in L. So first, we need to calculate the number of bits that would be required to get the desired SNR to be 42, because the signal to noise ratio is increased, so the SNR here will also increase. So we will make use of a very general formula, that is signal to noise ratio is equal to alpha plus 6n. So there are two ways to go about this. I will be telling you both of the techniques. First will be very easy to substitute the values and calculate the alpha here. So first, the signal to noise ratio is 30 dB. So we'll substitute 30 here. We don't know the alpha value, it's a constant. We don't know the value of n, that's the number of bits, that is 10. So here alpha will turn out to be minus 30. So after calculating the value of alpha, we'll now move to calculate the value of n for 42 dB. So we'll substitute here. So let me do it just beside it. So signal to noise ratio is equals to alpha plus 6n. This is 42. This is minus 30. This we have to calculate. This will turn out to be 6n is equals to 72, and will turn out to be 12 here. So you can see the value of n here has increased. So there are two ways to go about this question. So a similar approach to this question without going through this calculation of alpha would be that to understand the formula here. So the formula here says the signal to noise ratio is equals to alpha plus 6n. The formula here is saying for an increase of 1 bit here, the dB increases by 6. So you can see here, alpha here is constant. The thing here, 6n, is of quite importance. 6n is basically referring that if we increase the number of bits by 1, if bits are increased from, for example, from 7 to 8, for each bit increase, the dB increases by 6. So in the question, you can see the dB here is increasing by 12, and if each bit increases 6 dB, so to get an increase of 12 dB we will require 2 bits, for 6 bits for 1 and 6 bits for 2. So the original number of bits are 10, and increasing it by 2 will give us 12. This is the answer we also obtained from that calculation. So that's a simpler approach to go about it if you understand the formula. It's not required to use this kind of approach. You can go for the calculation approach as well. So now in last part we have to calculate the function increase in the transmission bandwidth required for this increase in L. So it's very easy. We know that 12 was the new bandwidth, dividing it by the previous subtracting by the previous bandwidth, dividing it by the previous n. I apologize, I will repeat this. This is the previous, this is the new n, this is the previous n, and this is also the previous n. So that turns out to be 20%. So the increase in transmission bandwidth would be of 20%.